This is a total production. Alright, hello Chem Minions. This is going to be our second practice video for chapter 5. So the first half of this we'll practice using IUPAC naming, and we'll include cis, trans, and EZ in the naming. So I guess more practice that way. And then also we will look at understanding the terms of nucleophile and electrophile. There's about four practice reactions on this page. Alright, so diving into naming. Alright, so as we look here at our first one, we have a 6-carbon chain, and then we have a 1, 2, 3, 4, 5, 6, 7 carbon, sorry, a 6-carbon ring and a 7-carbon chain. So our chain is going to have to be the parent. And based off of how things are looking, 1, 2, 3, 4 versus numbering this way, 1, 2, 3, looks like we're going to have to number this way, 1, 2, 3, 4, 5, 6, and 7. So it looks like we're going to have a heptene. You heard that E in there, right? So it looks like we're going to have a hept3ene, right? So because the first carbon to get the double bond is the third one. And then it looks like we're going to have a 3-methyl. So I'm going to write this up on the side. A 3-methyl and then a 4-cyclohexyl. Right, so for that, when we look at what goes first, it's going to be C versus M. So we're going to have to put 4-cyclohexyl 3-methyl. I'm going to squeeze this in. 3-methyl hept3ene. Now also, you notice that this double bond is tetrasubstituted. And so based off of our priority groups, on this carbon you have an ethyl and a methyl, so that's the higher group. And then you have a 3-carbon chain versus a 6-carbon ring, so the ring is going to be the higher priority group. So since this has 4 groups around the double bond, and they're on the same side, we're going to have to use Z in the name. Okay, so sorry, my Z got a little messed up, but this is Z 4-cyclohexyl 3-methyl hept3ene. All right. Now next up we have another chain, and it looks like I'm definitely gonna have to number here 1, 2, 3, 4, 5, 6. So it looks like we have a bromo branch and a methyl branch that's gonna come off. So we'll have a 2-bromo, and it looks like we're gonna have a 5-methyl. And then so there's our branches, and then this is going to be a hexene, so it's going to be hex2ene because that's the first carbon to see it. So I'm going to make it hex2ene. That's a number 2, not a Z. And then based off the priority groups here, because this is tri-substituted, 1, 2, 3 groups around that double bond. So you're first on this carbon, you're going to compare methyl and bromo, so it's the bromo group. And then here on this bottom carbon, you're going to compare a hydrogen versus all of this 4-carbon chain, and that's going to be the higher priority group. And those are on opposite sides of the double bond. So in this case, we would use E. Okay, since it's tri-substituted, we can't use cis, trans. All right. Next up, here we have a 5-carbon ring, so that's going to be a cyclopentene. Now, when we number, we're going to have to number through the double bond. So we're going to have to either start numbering 1 here and go 1, 2, 3, or we're going to have to start numbering 1 here up at the top and go 1, 2, 3, 4. So it looks like I'm going to go 1 here, 2, 3, 4. All right. So based off that, that means I'm going to get a 3-methyl and a 4-methyl. So it's going to be a 3, 4 dimethyl cyclopent, and I'm going to put the number 1 in there, 1-ene. All right. And then since the double bond's actually in the ring, we don't have to put Z or cis because this could be either one. It's in the ring, so we automatically know that it's that way, but some individuals may want you to go the extra mile and actually put that. So you could put cis or you could put Z. So there you go. I don't see the point in it, but anyway. Everything else except for the Z I think is necessary. In this case the Z is not necessary in my opinion, but that's just my opinion. Alright, next up, what do we got? We're going to have a chain, so it's going to be 1, 2, 3, 4, 5, 6, 7. We have a 7 carbon chain. Now here's the kicker. Do we start numbering 1 up here to get a 2-methyl and to get a 5-alkene, or do we start numbering 1 here? And so the question is, which one takes higher priority? One kind of quick and rule of thumb that doesn't always work, but since you're comparing a branch versus a functional group that changes the name of the parent, the thing that changes the name of the parent tends to take the higher priority. So it actually would be 1, 2, 3, 4, 5, 6, 7, that way. So we would call this hept2-ene, and then it would be like a 5,6-dimethyl. So because you got 2 methyl groups there. So this would be 5,6-dimethyl. And then we would call this hept2-ene. Hept2-ene. I seem to be loving the 7 carbon chains. That wasn't on purpose. Alright, and now also this double bond is di-substituted. So we would have to worry about cis, trans, or EZ. We could do it, it's di-substituted, so we could use either one. So you could put in here trans, or you could put E. Either one would work for this. Okay, don't do both, just pick one, trans or E. All right, and then for this one, I'm gonna name this one a little weird. So what I would do to name this guy, well, no, you have a 3 carbon chain and you have a 6 carbon ring, so the ring could take priority here. So one way you could name this, because this is a 1, 2, 3 carbon chain, so you could make this the branch and make this the parent. So if it was, so what would this be called? All right, so this is a pentene, not a pentene, this is a propene, right? That would be if it's the parent. But it's specifically a 1-propene. So what you could call this would be a prop-1-enol group, right, like that. And then so you could just call this, and then that would be carbon number 1 there. So you would call it 1-prop-1-enol cyclohexane. Okay. All right. Now it's important to put this one in there in particular because see the double bond is there at the carbon closest to the parent, right? Because notice here, 1, 2, 3, right? What if the double bond were there? Because then it would be prop-2-enol, right? So that's kind of important. Okay, this number 1. Okay, that number 1 is saying, hey, this group is coming off the first carbon here. Okay, all right. Next up, what do we got? We got another this is now a cyclohexene. All right, and so it's either going to be which of these 2 carbons is carbon number 1. Well, remember, it's pretty much both of them are the alkene. So the only difference now is the branches. You have a methyl versus an ethyl. So this starts with an E, that starts with an M. So alphabetically, E goes first. So this would be carbon number 1, and this would be carbon number 2. So we would label this as 1-ethyl, 2-methyl, and then we would have to use cyclohexene. And so you could name it 1-cyclohexene, like so. All right? Okay, so hopefully that naming helps you out a lot here. All right, next up we have some reactions. Now I've given you the reactants and the products, right? And so from here you have to identify the nucleophile, you have to identify the electrophile, and then you got to put in curved arrows to actually illustrate the mechanism. So in this case, you really just have to recognize what's going on here, right? We had a positive carbon and it's gone, right? Now there's a bond here with an oxygen. So you had an OH minus. So what does that mean? That means one of the double bonds on this oxygen attacked that carbon, right? Because you always start from electron rich, it attacks electron poor. So electron poor is easy to tell when it's a positive charge. Electron rich is easy to tell when there's a negative charge. So this would be the arrow to explain this bond forming, right? This arrow is in fact that bond forming. So how do you tell the difference between a nucleophile and electrophile? Well, firstly, we use Nu with a colon there, and then we use E with a positive there for electrophile. So electrophiles those electrophiles are electron lovers, right? What loves electrons? Positive charges. So this would have to be the electrophile. Nucleophile would be nucleus lovers. What's in the nucleus of an atom? Protons that have a charge, right? There's neutrons too, but we're talking mostly about protons. So nucleus lovers or proton lovers have to have negative charges. So that's why this guy's our nucleophile. Okay. Now if we look at this in terms of what's our nucleophile, what's our electrophile, we can see here, right? Didn't our nucleophile have a negative charge? Well, that has a negative charge too. So odds are this is our nucleophile and this is going to act like our electrophile. So in this reaction, remember, nucleophiles attack electrophiles. So here, OCH3, where does that go in the product? Well, it's bound to that double bonded carbon, right? So if you have to show the arrows, what I would expect is that a lone pair from this oxygen attack that carbon. And then what can you see happened? Is the chlorine still on that carbon? No, it got kicked off and now it has a negative charge. So that means this bond broke and went to that chlorine. So using the products, right, you should be, for now, right, once we get into chapter 6, you're going to need to be able to do this without seeing the products. But now seeing the products, you should be able to see what bonds were formed, right? An oxygen-carbon bond was formed right here, right? So that's that arrow. And then this bond had to have been broken because chlorine is broken off and it's got a negative charge, okay? All right, next up. What do we have? We have a nitrogen with a negative charge. We have a neutral thing with an oxygen. So what's the real difference here? So here the nitrogen had a negative charge, now it has a hydrogen. Here the oxygen had a hydrogen and now it doesn't. So what would I believe happened here? I would believe that the electron-rich thing, right, this nitrogen actually has 2 lone pairs on it. I believe that it attacked that hydrogen and then broke the oxygen-hydrogen bond to put those electrons on the oxygen, right? So what tends to be the attacker? The nucleophile, the thing with the negative charge. So this is our nucleophile, and then therefore this is acting like our electrophile. And that makes perfect sense right here, because if you notice, what's the difference? A hydrogen is changing. So if we go back to like chapter 2, we talked about acid-base chemistry, right? Acids donate protons, right? Here, this alcohol group is acting like an acid. It's donating a proton to the nitrogen, right? It lost it and donated it to the nitrogen. Acids tend to act like electrophiles, right? All right, and then next up, what do we got here? It says we have an N3 that's a minus. Negative charge tends to mean it's a nucleophile. I'm just going to go out on a limb here and say it's the nucleophile because it has a negative charge. And then here we have an alkyl bromide. Well, we notice over here the bromine is by itself. It's no longer there. So what that makes me believe is that this bond broke, right? And those electrons went to the bromine. So what caused that to happen? The N3 minus attacked the carbon here. Right? So in that case, that makes sense, right? The nucleophile attacked the carbon, and that's actually the partial positive location in this molecule, because in this polar bond, right, bromine's more electronegative. So the negative thing attacked the partial positive thing and kicked off the bromine, right? And so that would mean, that makes perfect sense to think of this as acting like the electrophile in the reaction. All right, so hopefully this kind of helps you guys with identifying nucleophiles and electrophiles. And also you got some help with naming and looking at EZ, cis, trans in that naming as well. All right, well, adios for now, and stay weird.